All right, let's talk about hardware design. If you've ever tried to write code for, say, an FPGA and just felt like everything you know from software is wrong, yeah, this one's for you. We're going to break down 3 unforgivable rules that will save you from, well, a world of pain.
So why is this so different? It's a question that honestly trips up almost everyone coming from a software background. Think about it. With C++ or Python, you're writing a recipe, a list of steps for a CPU to follow. Do this, then do that. But with hardware code, you're not writing a recipe at all. You're actually describing a physical thing, a circuit that's going to exist in silicon. It's a huge mental shift, and that's exactly what we're going to get into today.
Okay, so at the absolute core of all this stuff is something called register transfer logic, or RTL. And you know what? The name kind of gives it away. It's all about how data gets transferred between registers. Just picture these registers as tiny little boxes, flip-flops, that hold on to a value for just one tick of the clock. And the logic part, well, that's all the circuitry in between. You know, the AND gates, the OR gates, all the stuff that actually does the work and transforms the data before it gets to the next little box.
And this right here, this is the fundamental pattern. It's the DNA of pretty much every sequential digital design. You've got data sitting in a flip-flop, the clock ticks, bam! The data is released into this cloud of combinational logic that messes with it, transforms it. The result of that transformation then shows up at the input of the next flip-flop, just sitting there, waiting for the next clock tick to get captured. If you can get your head around this simple pattern, you're well on your way. This is the heart of RTL.
But, and this is a big but, to write code that actually builds this pattern correctly, you have to play by some very, very strict rules. We were inspired by a lecture from Professor Audie Terriman, who calls them the unforgivable curses of RTL. Yep, like from Harry Potter. And honestly, it's the perfect name, because breaking these rules will absolutely 100% doom your design. So let's get our wands ready and learn how to defend against the dark arts of bad hardware coding.
All right, rule number 1, the Imperio curse. And it's a simple one to say, but a huge one to follow. You do not put any logic on your reset or your clock signals. Ever. These aren't just any old signals, they're sacred. They're the conductor of your chip's entire orchestra, and you have to keep them absolutely pristine.
And here's why that's so critical. Look, in your normal data paths, you get these tiny little momentary flickers in the signal. We call them glitches. They happen all the time, and it's usually no big deal, right? They settle out before the clock edge comes along. But what if a glitch happens on your clock signal? Whoops, you just got an extra accidental clock tick that sampled a bunch of garbage. Or what if a glitch hits your reset line? Your entire system just randomly reboots. It is an instant, unrecoverable disaster.
So, okay, what does this actually look like in code? Let's check out this example. On the left, you've got the wrong way, which, let's be honest, it looks pretty intuitive, right? If reset is active, grab the input value. Makes sense. But here's the problem. That's logic on your reset. A physical flip-flop can only be reset to a hardwired 0 or 1. It can't be reset to some other signal that's changing all the time. To even try and build that, the synthesizer would have to create this horrible glitchy mess on your reset line. Now look at the right way. It's a little different. On reset, all we do is set a state machine to an init state. That's it. Then, on the very first clock cycle after the reset is gone, we're in that init state, and that's when we sample the input. See the difference? The reset itself stays completely clean. Moving on to our second unforgivable curse, the Crucio curse. And the rule is simple. Do not infer latches. Now, a latch is a memory element, but it's the kind you absolutely do not want. See, a flip-flop is well-behaved. It only changes on a clock edge. A latch is like a door with a broken lock. It's transparent, meaning whenever its enable signal is high, data just flows right through it. And that, my friends, is how you create absolute nightmares for timing analysis.
So how do you end up making one of these things by accident? Easy. You're just ambiguous. In a combinational block, that's your always at star, you have to tell the synthesizer what to do in every single possible situation. So if you write an if statement, but you forget the else, well, you've told the hardware what to do if the if is true. But what about when it's false? The synthesizer just throws its hands up and says, I don't know what to do, so I guess I'll just hold on to the last value. And to hold on to a value, it has to build a memory element. And boom, you've got yourself a latch.
The good news is, avoiding this is actually pretty straightforward. You just have to be disciplined. Number 1, every if gets an else, no exceptions. Number 2, every case statement needs to cover all possibilities, or you have to give it a default case. But honestly, the best way, the pro move that just solves this problem completely, is number 3. At the very top of your combinational block, before any ifs or cases, just assign a default value to every single output. That way, even if you miss a condition somewhere, the signal already has a value to fall back on. No latch, problem solved.
And that brings us to the final and, dare I say, the deadliest rule of them all, the killing curse of RTL. This is the big one. This is the one that trips up new hardware designers more than anything else. You must, strictly, separate your sequential and your combinational logic. And let me tell you, the stakes here are as high as they get. This isn't just, a stylistic preference. This is about writing code that you can actually read, that you can debug, and that turns into hardware that actually works the way you think it will. If you mix these two types of logic, you just create a tangled spaghetti monster of code that is impossible to understand, and you will, almost guaranteed, have to delete it all and start over. So, this is what that beautiful separation looks like. You have two kinds of blocks. The sequential block, the always at post-clock one. It has one job and one job only. Describe the flip-flops. Its whole purpose in life is to store the current state of your system. Then you have the combinational block. This is where all the thinking happens. It takes the current state as its input, does a bunch of calculations, and figures out what the next state should be. I love this way of thinking about it. The state is what you have right now. The next state is what you want to have on the next clock tick. Okay, let's make this concrete with a simple counter. On the left, the wrong way. See how that count plus one logic? That's an adder circuit, is mixed right inside the sequential block. That's the violation. Now, look at the right way. Oh, it's a thing of beauty. We have a completely separate combinational block whose only job in the entire world is to calculate the next count. All it does is the addition. And then look how clean and simple the sequential block becomes. It just says, hey, when the clock ticks, whatever is in next count, put it into count. That's it. Simple, separate, and most importantly, correct. All right. We've made it through the 3 unforgivable curses. So the big question is, how do you make sure you're not accidentally casting these spells on your own code? Well, you use a sanity checklist every single time.
So here it is. This is the checklist you can run through. Just ask yourself these questions about your code. First, are my clock and reset signals totally clean, only showing up in the sensitivity list of my sequential blocks? Next, does every single one of my ifs have an else? Are all my case statements fully covered? Then, is all my actual thinking logic inside a combinational always at a star block? And are my sequential blocks, well, are they almost boringly simple? And the last crucial one, is any given signal only being assigned a value in one and only one always block? If you can tick yes for all of these, you are well on your way to writing solid professional-grade RTL.
And really, that's what this all boils down to. To get good at hardware design, you literally have to unlearn some of your most basic instincts from software programming. You have to stop thinking about a sequence of commands and start thinking in parallel. You're not writing a script for a computer to follow, you're drawing a blueprint for a real physical machine. So the only question left is, are you ready to stop programming and start describing hardware?